So our speaker today is Arthur Bartels. His talk will be about K-theory of Hecke algebras. Please go ahead, Arthur.
Okay, thanks for inviting me. So I'll talk about K-theory of Hecke algebras, and this is joint work with Wolfgang Lück. So this is about, sorry, messed up. Totally disconnected groups. So by this, I mean that the group is a topological group and there's a countable neighborhood basis for the unit that consists of compact open subgroups. And the standard examples are, for example, the p-adic numbers, or maybe the p-adic integers, or the unit in theirs, or linear groups over them. And if
don't discrete groups satisfy that?
Oh, and discrete groups. But sort of, we won't focus on discrete groups. We'll be interested in the non-discrete groups. But it's true. Right, so, and if the group is compact, this means it's an inverse limit of finite groups. Right, so you have lots of finite quotients. And sort of the limit would be an example of such a group, but that would be a compact example. Okay, and then we're going to study the Hecke algebra of G, Hg, and it consists of all functions, complex valued functions that are locally constant and have compact support. And it's an algebra with respect to a convolution product. So the product of two functions evaluated at G is given by the usual formula. That we know from discrete groups, but since we have the topology, we need to integrate, so we need to pick a Haar measure on the group. But then it turns out that the algebra up to canonical isomorphism does not depend on the choice of the Haar measure. Okay, and in the discrete case, this just recovers for us the group ring. And locally constant doesn't mean anything on a discrete space, and compact support then just means finite support. And the convolution product is the usual product that we have on the group ring. Right, and in the compact case, then the Hecke algebra becomes a co-limit of group rings of finite groups. And something that took me a while to get used to is that this algebra, the Hecke algebra, is in general not unital, simply because the unit would be the characteristic function of the identity element, but this is not locally constant unless the group is discrete. Okay, so that's, at least for someone like me, first takes a bit getting used to, but it turns out that this is not so problematic because there are lots of idempotents. When you take U from the countable basis of the neighborhoods for E, take a small compact open subgroup take a small compact open subgroup period, take its characteristic function, and we can think of this as sort of, trying to approximate the characteristic function of the identity element, and then to turn it into an idempotent, one has just to normalize by dividing by the Haar measure.
Sorry, is a totally disconnected group automatically Hausdorff?
I think, with this definition, it is here. I'm sorry. If that's our definition, I think it becomes automatically Hausdorff, yes. All right. Another thing one needs to be careful with, if one has a non-unital ring, then maybe one shouldn't look at all modules, but add conditions. And one condition that's good is to require modules to be non-degenerate, which just means that if I take my module and I multiply it by all elements of the ring, I still get the whole module, right? This would be obvious if our ring had a unit. We could just multiply by 1 and recover any vector, but the requirement is that this happens regardless, right? And of course, these sort of these idempotents help in achieving this. Okay, and it turns out that this category of non-degenerated AG modules has also a different interpretation, namely as smooth G representations. So these are representations, complex representations, since we took complex valued functions, G acting on V, and the requirement, the smoothness requirement, is that for any vector, the isotropy group of the vector, right, stabilizer, is required to be open. And this has as a consequence then that any vector is going to be fixed by one of these idempotents, right? You just make the U so small that it's inside the isotropy of V. Okay, right. So there are two ways to think about categories associated to such a totally disconnected group. You can think about them as Hecke modules or as smooth representations. Right. And if you again take a compact group, then sort of properties we know of representations of finite groups survive. So in particular, first, they survive because if our representation is finitely generated over a compact group, then it ends up to factor over a finite quotient. So it's just a representation of a finite quotient. And this is then the consequence that the category of representations over a compact group is semi-simple. In other words, any representation is a direct sum of irreducibles. And moreover, the automorphisms, the endomorphism of a reducible representation are just C. So the category is as a category equivalent to an infinite sum of the category of vector spaces. Okay, so for compact, maybe life is not so difficult. And then for a general group, one tries to compare the two via compact induction. Maybe I should get rid of some of the yellow. Okay, compact induction takes the representation of a compact subgroup and induces it to a representation of the whole group. And one way to write down the formula uses the Hecke algebra. You just take this tensor product here. Okay, this way you turn representations of compact subgroups into representations of the whole group. And conjecturally, one tries to understand the representation category of G in terms of this functor, in terms of compact induction. More precisely, there is sort of one very old conjecture that says that a certain class of representations, reducer representations, so-called cuspidal representations, are compactly induced. It's not quite true. This is only true if the center is compact. And the other thing is that this representational category can be written as a product of so-called Bernstein blocks. And there the conjecture is that for each Bernstein blocks, there is a certain compact subgroup and a representation that sort of describes this Bernstein block. So this goes under the name of type theory. So let me just write. Yeah, these blocks admit what's called the type. Okay, but I don't want to go this route. And instead, we're going to look at K-theory. Right? And here is one possible definition for K0 of the Hecke algebra. We just take our category of representations and then do the usual thing. So saying we take isomorphism classes of finitely generated projective smooth representations, take the free abelian group, and then divide out the usual relation that splits any short exact sequence. So a short exact sequence, then the corresponding elements in this group satisfy the relation that kernel plus quotient is the guy in the middle. Okay, and then the functor that we had before, this compact induction functor here, gives us something in K-theory, but this we can do for any open subgroup or compact open subgroup, and so we sort of can put them all together and take a co-limit over all open subgroups and end up with a map. Is a map that compares the K-theory of the Hecke algebra with sort of everything we can cook up from compact open subgroups, right? And strictly speaking, we should be a little more careful in taking this co-limit that the co-limit is really over an orbit category. Okay, but for today, that won't be so important. Okay, and then there's of course also not just K0, but we have K-theory for all n indexed by n, and I won't be able to recall the definition. And then
yeah. So I mean, in the usual discrete rings and group algebras, in that context, to any subgroup of G, you can associate some algebra, which is the induced algebra, the ind sub G sub H upper G when H is a subgroup of G. Is there something akin to that in this context, and is the representations, are the compactly induced representations over this ring, the induced ring? So can it be thought that way? I mean, the ring will always not be non-unit, but
so you want that the ring captures all compact induced representations for a fixed subgroup U.
Yeah.
Yeah, and my guess is you take the endomorphisms of
well, I mean, if it has a small projective generator, then I think the endomorphisms of that would be, this would be a unitary ring. Right?
Yeah, I mean, that's maybe. Yeah, but this is what typically happens, right? Sort of, I mean, there are lots of unital subrings in, maybe I say this, right? I could have said this, where is it? Here, we have sort of lots of subrings as unit.
Coming from the lots of idempotents.
Yeah, exactly. And, you know, those are then typically written as, right, meaning functions that are bi-invariant for the action of U. And I think this ring is the endomorphism ring of the induction of the trivial representation. Right. But I'm not sure if this ring sort of captures all the induced representations. Okay, I think the short answer is I don't know. Where were we? Okay, I was gonna start talking about higher K-theory. So, you know, K-theory is defined for all, not just K0, but for all n. We have Kn for all n. And then there's an analog of this map here that looked at everything that's captured by compact open subgroups. And there's sort of two ways to do this. You could either say, instead of thinking about K0 as a group, we think about K-theory as a spectrum. And then this co-limit becomes a homotopy co-limit, and sort of you look at the K-theory spectra and put them all together. Or more algebraically, one can think of this homotopy co-limit really, I mean, its homotopy groups really are the homology groups, are certain homology groups, and we can put them instead. And that's what I've written here. Okay, so there's a similar map whose target is now Kn of the Hecke algebra. and it has as an input a certain homology group. Here, the space that is used is the classifying space for proper actions. And we can add smooth if we want to. All right, smooth would mean any point is stabilized by an open subgroup, but it turns out that sort of the universal space for proper action is already, or it can be made smooth. So those end up being the same. And then, so this is the whole gadget on the left. Let me write like this. The whole gadget on the left is a certain G homology. Let's put this theory as H maybe. All right, so Hn refers to a certain homology, and it can be computed, and that's sort of the last thing. Can be computed from certain values. So and what goes in is again K-theory of Hecke algebras, but now for compact open subgroups. And the catch is that you just don't need just the value at the nth K group, but all K groups, at least the ones of index lower than n.
Are the negative K groups of HU for U compact?
No, for compact not, right? Because as I said, that the representation category in the compact case is semi-simple. Where did I say this? Over here. Right, so this means rep U is really just a sum of categories, and each of these categories is just complex vector spaces. Because when you have a sum for all, right, you have a sum and for every irreducible representation. Okay, so these are right. So these groups, in a certain sense, they're fairly simple, right? You have to determine what are the irreducible representations, and then you have to understand what is K-theory of C. And if you're only interested in K0 or something, then that's not so difficult. Okay. Oops. Let me try to clean up a little bit. All right. Okay, so that's what I wanted to say about these maps for the moment. And from now on, we'll be much more restrictive for our groups, right? So we're not going to just take totally disconnected groups, but it's very special totally disconnected groups, namely, we take, oh, thank you. We take the F points of a reductive algebraic group over F, where F is a non-Archimedean local field. So maybe this doesn't mean much to you, and maybe it doesn't mean so much to me either. But the point is, the groups we had at the beginning are examples of these, right? SLN is a reductive algebraic group. GLN is a reductive algebraic group. And then you put in a field that is non-Archimedean local field, and this basically means it's QP or an finite extension of QP, or you could alternatively have a function field. Sorry. function field of a power series ring over a finite field. Okay, and the important bit for me is that for these groups, there is sort of a very nice space on which they act, the so-called Brouwer-Titz building. Okay. The Brouwer-Titz building is a certain simplicial complex, sort of built from apartments. And each apartment is just a flat space of a fixed dimension, and then they're put together in a certain combinatorial way. In particular, the flat geometry Rn has is inherited by the building, by the Brouwer-Titz building. So in particular, this is a Ket-zero space. Okay, and then the action has all the reasonable properties. It's smooth, proper, co-compact, and isometric. Okay, so this gives us a geometric way to understand the group. And in terms of what we've seen before, this space is then just a model for the classifying space for proper actions, E under bar G. Okay, and then in this case, if we make this assumption about the group, then one knows much more about Hecke algebras and representations. For example, Bernstein proved that the category of smooth representation is Noetherian and has finite cohomological dimension. So this implies in particular that, we just said this for the finite subgroups, that there is no negative K-theory, but the same is true for non-compact groups, for these non-compact groups. Right, so negative K-theory vanishes. And it also means, right, in my definition here, in our definition, I used projective representations, but since the representation category is Noetherian, has finite cohomological dimension, it has the required regularity property. That means any representation can be resolved by any finitely generated representation can be resolved in a finite way by finitely generated projective representations. And so we can use finitely generated representations instead of.
But is the equivariant homology defined if you take coefficients on K-theory or finitely generated representations? Is this functorial enough for the assembly map to be defined?
On the left, everything is projective, right? Because with the input is so easy.
Because the answer is simple. Yeah.
But I think it's also, the functoriality wouldn't be the issue here. I think you can, even if we didn't have this, we would get an assembly map. But I want to point out, so that was the reason why I wrote the relation in K-theory with short exact sequences, right? Because if we have projective representation and they split anyways, and we just talk about the relation for direct sums of representations. But if we talk about arbitrary representations, then we need to formulate the relation as I did here, by splitting short exact sequences. Okay, this is something Bernstein tells us. And then there's a result of Schneider and Stuhler that says for certain representations, for so-called admissible representations, and admissible means the following. You take your representation and take fixed vectors for a compact open subgroup, and you require the dimension to be finite. So for all we take fixed vectors under compact open subgroups, then the dimension should be finite. And then they have a way, actually, they use the Bartels building to cook up a finite resolution for V by compactly induced representations, by finitely generated compact, or by finitely generated compact induced representations. So in particular, if I can resolve my representations by compactly induced representations, then I'm going to be in the image of this map that we had before, alpha 0. And this tells us certain representations are in the image. But it's then just the alternating sum of the modules that appear in the resolution. Okay. And that studied this map that I have here on the level of K0, and he proved that it's rationally surjective. Oops. And he conjectured that it's in fact surjective. I mean, really, he made a weaker conjecture. Really, sort of it's, yeah. Yeah, sorry. So really the conjecture was about the torsion in K0 modulo the image of alpha 0. Oops. Where was I? Here. Maybe I put of alpha 0. Okay. But then he says, but maybe it's integrally surjective, in fact. Okay, and our theorem is, in fact, much stronger. Right? The map is, in fact, an isomorphism integrally, and that's not only true for alpha 0, but in all degrees. That's our result.
So this is for G as above. F
yeah. Still. I mean, maybe I should have emphasized this more. From now on, we only have these G's here. But really, so I mean, our theorem does not so much use, this algebraic structure. It uses this action on the Bartels building, right? So one can phrase the theorem as if G admits a smooth, proper, co-compact isometric action on a K0 space that has a little bit more structure, a little bit more combinatorial structure, then the assembly map is an isomorphism. But it is then an isomorphism for these groups. Okay. Okay, maybe I'm slow. Okay, my remark. So the result, I mean, we prove something more general, and then this more general statement passes to closed subgroups. And two often the left-hand side can be understood more explicitly. For example, example is if the group is SL2 QP, then it acts on the Bartels building, which is just a tree, the so-called bus. symmetry, and in this case, the fundamental domain is an interval, and there's 3 isotropy groups. Let's call them U prime and I. One of them is just SL2 ZP, and then U prime is a variant of this, and I is maybe I write it down. They roughly look like this. Right, so I has entries in ZP, but one of the entries needs to be divisible by P, and U prime looks like this. And then from this one gets a Mie-Vittori sequence for this homology group. Right, of the form. And here we have, let me write instead of the homology group, right, K-theory of the Hecke algebra. And then one has the K groups of the 2 compact open, maximal compact open subgroups, U and U prime, and they kind of meet in I. So algebra of I, and then it keeps going. In the usual way the Mie-Vittori sequence goes. Okay, so from the result, one of these has a chance to get more concrete information about K-theory of the Hecke algebra. Okay, and I wanted to talk a little bit about the proof, and to do so, I want to return to the discrete case. Right, in the discrete case, the Hecke algebra becomes just the group ring, and then we can do the same sort of game on the left-hand side, take the space E under bar gamma in this case, if I call the group gamma, and have a certain homology theory, and we have a similar map as before, and we're interested in studying this map. But the way this is done is by adding a guy in the middle that is sort of slightly more complicated version of the homology group. So this is the classifier. So sorry. The space is often called E double underbar G or gamma. This is the classifying space for actions with virtually cyclic isotropy. Right, so this homology group is in a certain way built from K-theory of group rings over virtually cyclic subgroup.
So in this case, you not expect alpha star to be an iso, right? But rather
I do. I'll explain it. Okay. So we've factored our map into 2 pieces, and the second one is actually sort of the Farrell-Jones assembly map. So let me put like this. So this map is what's called the Farrell-Jones assembly map, and it is an ISO for gamma acts on a ket0 space in the fashion described before: co-compact, isometric, proper, and so on. So the second map is okay in our situation, but the first one, sort of this one, is also an isomorphism, right? This is the consequence of the computation of K-theory, of these K groups, of these here. Actually, maybe, although it is typically not phrased this way, we can be a little more restrictive about the V's. We only need sort of V's that map to Z and have a finite kernel. Right, and in this case, it's really just the Bartels one. The Bartels one formula that computes these K groups, plus the fact that the group ring, the complex group ring over a finite group, right? That's a regular ring. This is it's as easy as we had it before. It's just a finite sum of copies of C. Okay, so we get two maps, and then we get this isomorphism here. Okay, and this sort of, I mean, so the first one is kind of classical, just uses this Bartels one decomposition, and the other one is the Farrell-Jones conjecture. This is true, and this is involved, but it all uses the original idea that Farrell-Jones had when they introduced their conjecture. In particular, it uses dynamics. It uses a certain geodesic flow associated to this geometric situation of the group acting on a K-zero space. And I won't be able to explain this in detail, but I want to say how the virtually cyclic subgroups arise in this context, or these V's arise. So the V arise as follows. So what's their geometric significance? So in this geodesic flow, one studies geodesics and then takes the space of all geodesics and associated to every geodesic and has a certain subgroup, namely the subgroup that preserves this geodesic and acts on it by translation. So these are all group elements for which there is a tau, such then for all t, if I multiply my geodesic with G, I've just shifted the parameter in the geodesic by tau. Okay. And this group, it's not difficult to cook up a map to Z. You just send G basically to tau. Right? Tau might not be an integer, so you have to normalize a little bit. But okay, that's how the virtual cyclic subgroups arise in this geometric proof using the geodesic flow. Okay, and of course, our plan is to try to do the same now for totally disconnected groups, and we still have our action on the building, which, as I said before, is K0. So we have all the geometric input that we had before, and we can, consider maybe these subgroups VC as before. With exactly the same definition, but now we're hitting a little snag, namely this subgroup. This is a subgroup. It's a closed subgroup, but in general, it's not going to be open. Okay, so the typical example is as follows for SL2QP acting on the Basset tree, a typical virtually cyclic subgroup. In fact, the typical stabilizer of a geodesic of this form is going to consist of diagonal matrices. Right, so it's just isomorphic to the units in QP, and the map to Z is the evaluation, and the compact subgroup is the ZP, is the units in ZP. Okay, but and you can see the subgroup is because of these. Sorry, because of these zeros. The subgroup is not going to be open. It's just going to be a closed subgroup. But this has the effect that now we can no longer view the Hecke algebra of this virtually cyclic subgroup as the subalgebra of the Hecke algebra, right? Because we cannot extend by zero. That's the functoriality we have for group rings. If we think about elements of group rings as functions, then we just extend by zero if we have an inclusion of a subgroup. But if we here extend by zero, we get, this would be not locally constant. Okay, so while the geometry is all in place, yeah, we have the action on the building, we don't quite know what to put here, what we had before, right? We don't know what is the contribution in the K-theory associated to these virtually cyclic subgroups. Okay, but of course in K-theory of operator algebras, of C-star algebras, you're probably used to this phenomenon, right? If you have a topological group and the reduced C-star algebra and consider Baum-Kohn, then also the definition of the left-hand side is a little more complicated. Right? And it does not just depend on compact subgroups, but also on the way the compact subgroups sit inside the locally compact group. Okay, and so it's natural to expect something like this to happen again. Okay, and yeah, maybe I say a little bit of what we do. Okay, so you could first guess that we should just look at sort of functions in the Hecke algebra who support, well, it can't be V because V is a closed subset, but it could be a small neighborhood of V. Okay, but of course that's not a good definition because once we fix the small neighborhood, it's no longer going to be a ring because under composition the neighborhoods will start adding up, will get bigger. Okay, but a trick that allows us to get around this, or to sort of take a limit where the neighborhoods get smaller and smaller, comes from K-theory delooping. So
there's a typo, you meant Wagoner, right?
Sorry?
You meant Wagoner, right? It's a typo.
Where did I miswrite?
Is Wagoner and not Wagenor.
Did I misspell Wagner? Is that the? Yeah.
Yeah, it's Goner.
I see. Okay. Thank you. Like this, yeah. Okay, that's a bit embarrassing. Okay. Anyways, here's the looping. Can be described as follows. You sort of given a ring, you build another ring. Consists of column and row finite matrices over n, right? So it's kind of like you have a fat neighborhood of the diagonal where there might be entries, but then away from this neighborhood of the diagonal, you don't have any entries. And then you divide out the finite matrices and get a suspension ring. And Wagner proves that this is the K-theory of this suspension ring is the K-theory of the original ring, but shifted by one. All right, and the reason for this is sort of this lambda, this ring lambda of R, this cone ring. There you can swindle because you have infinite sums. Okay, and now we can sort of, for this suspension ring, we can sort of build something that makes the neighborhood smaller and smaller. Okay, and therefore, we pick a metric on our group, and then we form sort of alpha delta balls. So we think of alpha as large, alpha is sort of the direction of the subgroup, and delta is the direction which we thicken, right? So this is just the delta neighborhood of the alpha ball in V. This is what I've written here. Right, so I mean, in pictures, I have the unit element, and then I have V, which maybe I think of as something a little bit like a geodesic, and then the elements I'm allowing need to be close to V, and the point in V that we're using is at off distance at most alpha from V. Okay. And then I can make this construction first of this cone ring, sort of relative to this V. Well, that's now really a subring. That namely allow elements in Wagner's cone ring, but I require, that for some alpha, then if I fix some alpha, I can fix some alpha such that then for all delta, the support of the entries, the Aij, maybe I should, the Aij is contained in such a ball. It can be large bounded, but large in the V direction and small transversely. And how small becomes, smaller and smaller the more Aijs I consider. So I want this requirement for all, but finitely many Ij. And this then ends up being a ring. I can take the same quotient as before, and then this Wagner delooping still kind of works. So, I mean, I've now defined a subring, and if my subgroup is open, then it's not difficult to check that this construction just gives me the delooped ring as before. Right. And then I can deloop everything once and put sort of these variants of the delooping into the machine. And then I have at least a factorization that I can put at this spot here. Right. And then I still have to prove that sort of we can still run this Farrell-Jones argument on the right to get the isomorphism. And on the left, it becomes now more complicated because we made the rings more complicated. We need to prove that we still have enough regularity to get the isomorphism on the left. And I think I ran over, sorry.
Okay, thank you very much, Arthur, for a wonderful talk. Do we have any questions from the audience? I have a little comment. So in the, if I'm not mistaken, in the discrete group case, what you said implies that if the Farrell-Jones conjecture is true for a group gamma, and then the group algebra over the complex numbers, or maybe even over any regular ring, is K-regular.
Yeah, so this is the point, right? This is this here.
Yeah.
So, I mean, yeah, I think it would also work, right? If you took rational coefficients, but you need to invert. You need to invert the group, the order of the finite subgroups in your in your coefficient ring, and it still needs to be regular.
Mhm.
I think the precise condition is you want Q contained in R and R regular.
Okay. And does this or something akin to this still apply in the Hecke setting? The Hecke
In which
algebra
setting?
Sorry, we are next to an airport here. So in the Hecke algebra setting, is there
Yes.
an analog of this irregularity following from the fact that the assembly map is an isomer? Because I mean, you need to be able to consider Hecke algebras over the polynomial ring.
Now. So what is the exact statement you're looking for?
So is the Hecke algebra of a group for which your assembly map is an isomorphism automatically K-regular?
Oh, and K regular means means no nil terms?
Yeah, K-regular means that K of A is K of A of T. Yeah.
I think this is going to be true.
A of T1, Tn, I mean, yeah.
Because we can sort of cross our group with Z, and then we need that the conjecture is still true after crossing with Z, but at least our geometric assumptions are still going to be satisfied because we can just cross the building with R and then prove the isomorphism, and then get this assembly isomorphism. And then I think you should probably get out that there are no nil terms, because you have sort of the other formula to compute the K-theory of, the raw polynomial ring over the Hecke algebra. So I guess you're right. I guess you can get this out. Yes.
Yeah, so just one comment in Wagner's original paper where he shows this result of the suspension.
Yeah.
I always there are other models for this cone ring.
Yes.
There is this one name used by Karoubi, which imposes more conditions on the matrices. And I always call this the one Wagner chooses Wagner's cone ring. However, in his paper, he cites it from a joint paper with Farrell.
Ah, interesting.
The same of the Farrell-Jones Conjecture.
Interesting. And I mean, in fact, we're not really using this model for. I mean, this what I explained here is just sort of a rough idea how one
I mean that
gadget
picture
in the
is
middle.
not the picture of Wagner's cone.
Yeah, but yeah, we certainly use the delooping. We're working with additive categories, and we're using the sort of the Petersen-Weibel delooping.
Yeah.
But which in essence builds on the same idea.
Yeah.
I have a question, a technical question. Is this work on the archive?
No, we're terribly slow. I mean, I feel we're almost done, but I've felt this for a while. So
okay.
Sorry.
Thank you.
So, but it will be eventually.
It certainly, yes.
I mean, eventually at the end of time, so eventually.
No. I think, I was hoping before Christmas, but now it's going to be after Christmas, next year sometime. Yeah,
okay.
Yeah.
Yeah. It looks interesting.
Pardon?
It looks interesting.
Okay, thank you. Yes. I hope so.
Okay.
It certainly kept us busy.
Yeah. So if there are no further questions from the audience, I will stop the recording.